Morning. We start our lecture right now. Others will join us later, but we have to move on. So today we are going to be looking at DC machines. Basically, it will be an introduction. So we are touching on things that are common to both generators and motors. Right. So in electric machines, we know that there's conversion of energy from either mechanical to electrical, that is in a generator, or from electrical to mechanical, which happens in a motor. So those are the conversions that we get when we are dealing with our machines. So in the electrical side, we'll be looking at current and voltage basically. And then on the mechanical side, we'll be looking at torque and speed. So those are the main quantities that we'll be looking at when we're dealing with our electric machines. Right. But then there is a link between the electrical and the mechanical component. And that link is the magnetic field. So you realize that the mechanical side and the electric side are coupled by a magnetic field. So as you can see, if we are moving from the electrical system to a mechanical system, that means we are in the motoring mode. So we have electrical energy supplied as voltage and current. Then the output will be torque and speed, which are the quantities which we consider. But then when we are in the generator mode, we'll be moving from torque and speed being converted to voltage and current. So those are the things that we'll be looking at in our conversions. So our coupling medium is the magnetic field, which will be in the motor. So that will be our coupling component, which is the magnetic field. Right. So what you have to always remember is that when we are talking about electrical side, we are talking about the voltage and the current. When we are talking about the mechanical side, we are talking basically about the torque and the speed. So realize that we talk more of voltage current characteristics and also the torque speed characteristics in our electric machines. So since we are coupling using a magnetic field, then there should be electromagnetic conversion, right? So that we have a conversion from electric to mechanical. So there should be electromagnetic conversion. And when we talk about the voltage, then the induced voltage that we get out of the generator is according to Faraday's law, where we talk about the movement of a conductor in a magnetic field or the change of flux linkage to a conductor. In the polarity, we use Fleming's gradient rule. We talked about that in the previous lecture. And the magnitude of the induced EMF in the generator will be equal to BLV, where B is the flux density of the magnetic field, L is the length of the conductor in the field, and V is the speed at which the conductor is moving in our magnetic field. So as you can see, you realize that the induced EMF increases with the speed and also with the strength of the magnetic field. So here, if you apply Fleming's right-hand rule, you can see this motion, then the field in the induced voltage. And also bearing in mind that this represents field moving out into the plane, right? And so these quantities will basically be at 90 degrees to each other. And then you can use your Fleming's right-hand rule to get the directions. So this is very important. There's basically no other way you can tell about this direction of induced EMF unless if you use that right-hand rule. So it's very important to remember it. I explained it in the previous lecture. Then there's also the issue of the electromagnetic force, which gives us the speed and the torque. That means we are moving from the electrical side to the mechanical side, that is, we are motoring. The force is exerted on current carrying conductors. Basically, this is due to the interaction of the magnetic field due to the conductor and also the magnetic field in which the conductor is placed. So the direction of the force, which becomes the direction of motion of the conductor, is given by Fleming's left-hand rule, right? So Fleming's left-hand rule, just now saying the second finger, the current, the field, first finger, the thumb will point in the direction of motion. Then the force is called BIL, right? B being the magnetic flux density, I being the current flowing in the conductor, and the L being the length of the conductor. So that will be the magnitude of the force exerted on the current carrying conductor. So we look at the structure of the electrical machine. It is basically the stator, the rotor, and these are separated by the air gap. So there's the stator, there's the rotor, and these are separated by the air gap. So in that structure, this becomes our stator, which is the stationary part of the machine. And then this becomes our rotor, which will be the rotating part of the machine. And this, what is between the stator and the rotor, is the air gap. So that's the basic structure of our electric machine. There is an air gap between the rotor and the stator. And we have different types of windings that are involved in this conversion, right? With the armature winding, in which we refer the generated voltage. And then we have the field winding, in which we refer the magnetic field. So basically, the armature is the one which is, we talk about the electrical quantities that are there. Then the field, we talk about the magnetic quantities. Basically, the most important thing on the field is the flux and hence the flux density. So the armature winding and the field winding, they are not fixed. Like you can't say the armature should be on the stator or on the rotor. That depends on the construction of the machine. So you could find the armature windings wound on the stator and the rotor windings and the field windings on the rotor and so on. That is a matter of design principle, right? So take note that the rotor and the stator can either have the armature or the field winding in your electric machine, right? So what are the uses of electric machines? Basically, when we're looking at DC machines, are found in many uses in the conveyors. They are there in cranes, in paper mills, in textiles, and so on, in locomotives. Most of those things, they basically use DC machines in the order of hundreds watts and or horsepower and so on. I'm sure you know how to convert from horsepower to watts and watts to horsepower. So basically, the construction of the DC machine, remember we said we have the stator, which is mainly the outer side, and in this case our stator is made of the one which is our field winding, so that we have the North Pole here and the south pole there on the stator. So these windings in blue will give us the field windings, and then they will produce a flux that will cut the A gap and also the rotor. And in that process, we also have the armature windings. In this case, our armature windings are on the rotor, and hence the magnetic field will be cutting these armature windings, which are given in purple. Then there are axes, which are given, referred to the d-axis, which is the pole axis, and then the q or the quadrature axis, right? And then this midpoint between poles, we normally call it the interpole. That means we expect no overall electromagnetic induction on this line. That's why you see that they are a blank. That will be the interpole. We'll refer to it later when we talk about commutation and other stuff. So we go into the principle of operation of the DC motor or the DC generator. Basically, it should have poles. You can have different number of poles. In this case, we only have 2 poles, the north and the south pole. Then we should have conductors which should be able to move within the magnetic field. So as you can see, our field will be going in that direction from the north to the south pole, right? Then we have conductors which should be able to move in the magnetic field. So what are we looking at now? We are now saying when you cause motion, right? That means when you rotate the conductors, right? They cut the magnetic field and you have an EMF generated between 1 and 2. In that case, you are using the machine as a generator. But then when you induce a current here in the conductor such that the conductor will experience a force due to the magnetic field, the conductors will start moving in the magnetic field. And that movement in the magnetic field tells us that we are in the motoring mode. So if you use electricity to produce motion, you are motoring. If you use motion to produce electricity, you are generating. So that's basically what happens. So here we are just giving an illustration of the flux density of on the poles. So the north pole, the flux density, as you move your conductor in the angular movement, we are saying this will be 90 degrees. That means they will be cutting the flux at 90 degrees. This will be at 180. That means they will be in parallel. Here they will be cutting on the other side. That's 270 degrees. And they are back to 0 or 360. Again, they are in parallel with the field. So the flux will also increase in like manner. And since the generated EMF is also proportional to the flux, then you realize that the generated EMF waveforms tends to follow the flux. The generated EMF tends to follow the flux. Then we now go on to the voltage across terminal 1 and terminal 2. Right? The voltage across terminal 1 and terminal 2 for a 2-pole machine will also come in pulses. It comes to 0 when the flux is 0. When the flux reverses, it also goes up and comes to 0 again. This is possible because a DC machine uses what we call split rings. So these are the split rings. The split rings enable the current to flow in one direction. That means as the conductor changes from the south pole to the north pole, the split ring connected to it will now be connected to the positive, and hence current will still flow in the same direction. Again, we'll give more details about that. But for a multiple pole machine, you realize that the flux density now will also tend to overlap, right? So here instead, in one revolution in a two-pole machine, you only have one cycle of the flux density. But in a multiple pole machine, let's say in a four-pole machine, you have two revolutions of the flux in one mechanical revolution, right? And so if you increase the number of poles, you realize that the overall output voltage will just have some ripples, but almost a DC voltage, right? So the most important thing to take note of when you are looking at either the motor or the generator, if it is DC, it uses split rings and brushes. It uses split rings and brushes as the contacts between either your load, if it is a generator, or your source, if it is a motor, with the coils. You use split rings. So split rings, they will also change positions with the coils, conductors, so that the direction of the current remains the same. Right. That is a very important point to note. So multiple pole machines will give you smooth running, right? Because now we have more cycles of the flux in one mechanical revolution. We also have less variations in the induced EMF or in the force exerted on the conductors, and hence they become smooth running. So this is the structure of a four-pole machine. You realize now that there's two south poles and two north poles. That becomes a four-pole machine. So when a conductor moves from the north pole to the south pole, it completes one revolution of the flux, right? When it moves now from the north to the south again, it makes those changes. So it has more cycles of the flux than in the two-pole machine. So one mechanical cycle of a p-pole machine produces p over 2 electrical cycles. That is what I was explaining, that in a two-pole machine, you have one cycle and one magnetic cycle. In a four-pole machine, you have one mechanical cycle giving you two magnetic cycles. So if a machine is p poles, it also requires a p-pole armature. Then the electrical degrees will be called P theta m over 2, where theta m is the mechanical degrees. That means the number of degrees that you turn in the mechanical, right, will be equal to twice the electrical over the number of poles, right? So that is what we saw from figure 8, right? So we can determine now the pole pitch, which is the angular distance between two adjacent poles. We'll come back slightly. So the electrical distance between two adjacent poles becomes your pole pitch. From the north to the south, this will be your pole pitch, right? In electrical terms, one pole pitch is equal to 180 electrical degrees, right? So pole pitch in electrical terms is always 180 electrical degrees, because in electrical terms, when you move from one north pole to the other, you're going through 180 degrees. In mechanical terms, one pole pitch will be 360 mechanical degrees over P, where P will be the number of poles. So that is the pole pitch in electrical terms and in mechanical terms. So electrical terms, pole pitch is always 180 degrees. Mechanical terms, it changes with the number of poles, right? Then coil pitch now becomes the angular distance between two sides of a coil. The angular distance between two sides of a coil. In most cases, you realize that the coils might be wound for a two-pole machine, they'll be about 180 degrees from each other. A full pitch machine is one coil pitch equal to one pole pitch. So that means in electrical terms, coil pitch will also be equal to pole pitch for a two-pole machine. But then the DC machine armature windings are usually full pitch. That means the coil pitch, the angular distance between the sides of a coil will be usually always equal to the angular distance between the poles. Right. Now, when we are talking about armature windings now, remember I said in the armature, that's where we talk about the voltages. The armature, the induced voltage and the like, that's in the armature, induced EMF. So this is a conductor, right? So its ends are connected there, right? Then this becomes a coil with more turns to make up one coil. And then when the coils are connected one after another, then they produce a winding. So in our machine, we don't have a single coil. So we talk about windings in terms of machines. So these windings now, they will be positioned differently in the machine, and that will also determine the type of machine and what we expect in its operation. So this is a turn, this is a coil, and this becomes a winding. So a coil is made up of many turns, and a winding is made up of many coils, right? So there are different ways of winding the armature. There's what is called lap windings. So in lap windings, the coils are connected in series around the armature, right? That means all coils are connected in series around the armature. Then for speed, right. So for a P-pole machine, it will require P brushes for a coil to commutate P times. We'll explain what we mean when we talk about commutation. So if we have two poles, we also need two brushes for the coil to commutate. If we have four poles, we also need four brushes for the coil to commutate twice. So brushes are evenly spaced around the motor periphery. That means if we have two brushes, there will be an angle of 180 degrees between them. That will be a two-pole machine. Four-pole machine, then the other one will be added. There will be 90 degrees to each other, and so on and so on. That is the arrangement that we have in the brushes. Then the side of the coil are at interpole position during commutation. So when we talk about commutation, we are saying the current in the coil is now changing direction. So that is commutation. So we are saying the design of the machine should be such that when the current in the coil is changing, then there is no overall magnetic field experienced by the conductor. So it should be at at interpoles. So this line, these two lines which I have drawn now, will show us the interpoles. That means during commutation, we expect our brushes to be such that the sides of the conductor are at these points at interpole, so that they have basically zero voltage across them when they are commutating. Then brushes that make a positive set are connected together, and the same for those making the negative polarity. And coils between adjacent brushes are in series, right? So any coils that are in adjacent brushes, they will be in series, and the winding is therefore divided into P parallel parts. So if you have two poles in a lap wind machine, you also have two parallel parts in the lap wind machine. And in that, 1 over P of the total number of coils are in series, and their total induced EMF appears across the brushes. So if we have two poles, if we have a two-pole machine, then half of the coils will be connected in series. Okay? And then we have two parallel parts. If we have a four-pole machine, then 1/4 of the coils will be connected in series, sorry. And yet we have 4 parallel parts. That is illustrated there. So if we were to unroll a winding which is lap wound, then you will find out that the coils will be connected in series, right? And then the brushes will be such that they will be at a position where when the coil is turning, it will be at interpoles so that it doesn't have a voltage when it is changing the direction. So these will be our coils. We can say coil number 1, number 2, number 3, number 4, just for interest's sake. And they will all be arranged in series in a complete loop, but such that the sides of the coils which make negative polarity will be connected to the negative together, and the sides which make positive polarity will be connected together, right? And we said 1 over P of the total number of coils will be in series at any given time, right? And then the coils that are on adjacent sides of the poles, that means the ones here and there, they'll be connected in series so that when current flows from here, this one will also have current flowing in that direction, right? So one side becomes the negative, the other side becomes the positive. So these are the commutator segments. They are also arranged such that when there's commutation, the brush is connected to the coil will be in interpoles. So this will be 1 over P of the total coils connected in series, and we have P parallel parts. So this is the electrical equivalence of a lap wound machine. So if you have any calculation to make, they will be basically based on this kind of circuits. Right? Then there is also what is called wave winding. So in wave winding, again, the coils are connected to the commutator segments, which are 2 pole pitches from each other. So we are saying from north to south, that's 1. From south to north, that's 2. So the coil terminals are connected to commutator segments, which are 2 pole pitches from each other. And the coils are connected in series around the armature, just like in lap windings. Then for a P-pole machine, it will require P brushes for the coil to commutate. That is the same thing, even in lap windings. And the brushes are arranged as in lap winding. That means they are evenly spaced around the machine periphery. And the coils between adjacent brushes are again in series. and the winding is therefore divided into two parallel parts. So in wave winding, the number of poles doesn't matter. We will still have two parallel parts. That means half of the coils will be on one path, and half of the other coils will be on the other path. So we only have two parallel paths when we are talking about wave winding. So basically the difference between the lap and the wave windings is that in wave winding, we have, sorry, something went wrong. Just a minute. Okay, so I was saying in wave winding, the only difference between wave winding and lap winding is the issue of the parallel paths. So in parallel paths, we are saying in wave winding, we only have two parallel paths. In lap windings, the number of parallel paths depends on the number of poles. Okay? In lap windings, the number of parallel paths depends on the number of poles. But in wave winding, the number of parallel paths is just equal to 2. Otherwise, the connection is almost the same in both cases. Right. Then we'll take a break. We'll use the same link to continue with the lecture. Then we'll start on armature windings generated voltage. So we can take a break now, maybe a 10 minutes break. We start at 1:10. Thank you. We end here for the break.